Hi guys, I just want to finish chapter 7 up, and we'll be starting chapter 8 tomorrow on your blog, so I'll post a video beginning chapter 8 a little bit. I want to review back just talking about conservative forces because we're going to talk also about non-conservative forces. So a conservative force is just a force where the net work is going to be zero. It's a force where the path taken by the particle, the work done is independent of path. So my initial and my final positions are really what is what we should take into account if we're thinking about the work that's being done. And if my initial y is equal to my final y, let's say we have a vertical displacement, then that means that the net work is going to be zero because I'm ending where I began. So conservative force is just where we are independent of the path taken by a specific particle, and if we have a closed path where yi equals yf or my xi equals xf, then that work done by this conservative force is simply going to be zero. Some examples of conservative forces would be gravity, as well as the spring force, because ultimately we'll stretch a spring, but it started at its equilibrium position 0, its final will also be its equilibrium position 0, so that xi, xf are going to be the same. Now, gravity is also an example of a conservative force, because if we throw a ball up into the air, and we think about the work that's being done by gravity on the ball on its way up is going to be a negative mgh, if I'm thinking about its potential energy. On the way down, though, the energy is going to be a positive mgh, because now gravity is acting in the same direction as its displacement. So if we're thinking about then the net work that's done in terms of its potential energy, then that net work is going to be zero, because ultimately it's going to end right where it started. So just like we saw in the last slide, we can associate a potential energy for a system with any type of conservative force that's acting between members of the system. We can only do this, though, for conservative forces. So this is, in general, the work done internally. So when you have W and then in subscript INT, that's just talking about the work that's being done internally or within the system. That shouldn't be a negative capital D. It should be negative delta U, meaning that change in potential energy. So like we saw last for the gravity, if we're talking about gravity as a conservative force, remember that if we throw a ball up into the air on the way up, it would be a negative mgh, and that's just because gravity is acting downward while the displacement is upward. So it has to be a negative because the work being done here, they're in opposite directions. Now, if we're thinking about once that ball reaches once that ball reaches 0 up at the top, its maximum height, the ball is going to come back down, thus being now a positive mgh. So when it ends at the same position as where it began, my net work then, that work internal must be then equal to 0. So positive work done by an outside agent on a system usually causes an increase in the potential energy of the system. Now, let's see what would happen if we talk about non-conservative forces. So when we have if a conservative force means that it's independent of path, then a non-conservative force is where path is going to take an effect. So ultimately, non-conservative forces are going to act in a way that we're going to cause a change in the mechanical energy of a system. So non-conservative forces cause a change in the mechanical energy of a system. Well, what is mechanical energy? Mechanical energy is simply all of the kinetic energy plus all of the types of potential energy. That's what mechanical energy is. Non-conservative forces are path dependent. So path does cause an effect if we're talking about a non-conservative force. It does play a part here. Now let's take, for example, let's say that we have a crate that's moving along a surface, some horizontal surface, and I have another crate, the same crate with the same mass, moving along the same surface, but now we're going to move it along a larger displacement. So let's say that we're looking at just this first one here. This one, I'm going to have some form, let's say that friction is taken into account here. Now, friction is going to act along this surface, and ultimately it's going to slow that crate down, let's say. It's going to decelerate. This box, this crate, same mass, same surface, friction is going to act still, but it's going to act in a longer displacement. So because friction is acting in a longer displacement along this one, there's more work being done on this particular system than this one. So friction would be an example of a non-conservative force because friction is acting along a longer path in this case than in this case where the displacement was much shorter. So we can say more work would be done here. So that means it would be a non-conservative force. Ultimately, we would see as well, because in the last video we talked about that internal energy, that mechanical energy here is going to be lost because of heat energy. So we're going to have some type of internal energy instead. So we're losing mechanical energy in this one. We're also losing mechanical energy in this one as well, but we're losing more mechanical energy to heat energy, to that friction, in the longer that crate is going to be moved along that surface. So again, we can just see that in the figure to the right, we have friction acting on the book as it's moving across that table. Now, ultimately, we have two different paths. We have A, the brown path, which is much longer than B here at my blue path. So because friction is a non-conservative force and non-conservative forces are path dependent, we're going to have more work done in moving the book along that brown path, along path A, than we are moving it along the blue path, path B. And that's just because non-conservative forces are path dependent, and because it's moving a farther, ultimately it has a longer distance that it's traveled, so I'm going to have to be doing more work along path A. Okay, so we have said, guys, also, what is all of this? I don't know why my slide kind of messed up all of our formula here, so let's rewrite it. When we think about work done within the system, we can think about it as being equivalent to the change in potential energy. We can also think about that as being, let's say, work internally. We can also think about it as the integral from that initial to that final position of Fx dx. Now, this is just showing us that ultimately for a conservative force, the work really truly only depends on the initial and the final coordinates, which is why I have my initial x and my final x. All right, so if we just said that to find work, when we think about something done in the system, we said that was just equal to the integral of fx dx. Or we also said we can think about work done internally is just equal to that change, that negative change in potential energy. So if the work that's being done is equivalent to that change in potential energy, and we can also say that we can find that work done internally by taking the integral of fx dx, then to find x, I could just take the derivative then of potential energy of U. So if we wanted to find the conservative force, we can relate it to the potential energy function by saying that Fx is simply equal to the that derivative of potential energy in respect to x. Okay, so again, let's go through and see how these things are related. So let's say, let's look at example a deformed spring. So we can say Fs equals what we've supposedly said, du over dx. Now, we know that if this is a spring, I want to think about the potential energy in terms of a spring. We know that we can find also the work done by an external agent on a spring, because we know that also that's equal to that 1/2 kx squared. So let's rearrange this and say, let's actually find the derivative in respect to x for 1/2 kx squared. If I do that, then that should give me Fs equals a negative kx, because my negative is still out there, sorry guys, a negative kx. Well, we know that the force, for the spring is equal to a negative kx. That was just simply Hooke's law. So this just shows that we can derive our formula for springs, Fs equals our negative kx. So it's just showing that potential energy is an important function because this is a conservative force. We are conserving force here, and we can show that from deriving it. Guys, the last thing that we need to talk about are just another type of energy diagram, but in terms of stable equilibrium and also unstable equilibrium. So let's go back and think about our spring. We can graph the potential energy versus the position of a member of the system. And we're going to do that we're going to look at some of those in the next few slides. But we know that during, if we have a spring mass system, we can stretch the spring, we can also compress the spring, but ultimately that mass is going to oscillate between a maximum position that it can stretch out, and then also kind of a negative displacement where we can compress the spring so much. So I can think about that the block's going to oscillate between this maximum and then also between a specific amount where it's compressed at its maximum capacity. And it's going to continue to do that until it reaches that x equals 0, which is just that restoring position. So we always want our mass to be at x equals 0, that equilibrium position. So how would we graph that? Well, let's look. All right, guys, so if we graph the potential energy as a function of x, in this case, if we're talking about stable equilibrium, then that happens when our potential energy is a function of x. So when we're talking about ux, for the system is at a minimum. So when we're at stable equilibrium, then ux for the system is at a minimum. Now, let's look at when we're talking about our potential energy. Let's just say it's for a spring, because that's what we're focusing on that last slide. So potential energy in terms of a spring, ultimately we know that at x equals 0, that's where we're going to have that equilibrium point. Let's say that we stretch the spring out. Some external force is going to come and stretch the spring from equilibrium. And maybe it'll stretch it to where we get at x max. We know that x is going to be a positive value, but again, our force that's exerted by the spring is going to be a negative value. So it's going to accelerate it back towards that equilibrium position of x equals 0. If we compress the spring, so some external force is compressing the spring, if we have some external force compressing the spring, then we know that x is going to be negative, but the force is now going to be positive, again bringing it back towards that equilibrium position. So the block is going to oscillate between that negative x max and x max, and these are going to be called turning points. So remember that for a stable equilibrium, if we're going to draw some potential energy as a function of x, then we have to correspond that when u sub x is a minimum. Okay, so let's say that now, instead of having something at a stable equilibrium, let's say that something has an unstable equilibrium. Well, what would that graph look like? Again, let's model that that the force in terms of the x direction at x equals 0 is 0. So in that case, we know that our particle is just at equilibrium. Well, unlike a spring, when we stretch a spring or if we compress a spring, ultimately we know that that spring is going to go back to its equilibrium position. When we're talking about unstable equilibrium, then any other value of x, if we move something away from where x is equal to 0, then it's going to move away from that equilibrium position. And in that case, that's where we call it an unstable equilibrium. We can see from our graph that if x is greater than 0, we're going to have a negative slope. And if x is less than 0, we're going to have a positive slope. An example of this would be if we try to balance a pencil on its very point, then any place that we move it other than from that exact point where we could say x equals 0 is going to be some movement away from that equilibrium position. So then that would be an example of unstable equilibrium. Lastly, we just have to talk about neutral equilibrium, and that occurs in a system, in a configuration, when the potential energy is constant over some region. Typically, a small displacement from a position in this region will produce neither restoring nor disrupting forces. So ultimately, neutral equilibrium only arises because potential energy is just held constant over some particular region. So an example could be like a ball lying on a flat horizontal surface. That would be an example of neutral equilibrium. Okay, so in terms of Chapter 7, we are done. I posted some Chapter 7 multiple choice practice questions on your blog last night. I would like you to try those out. I'll post the answers to them, to those multiple choice questions on your blog. If you have any questions on them, you just either email me, we can work before school or after school, just let me know. And make sure that you check the blog again tomorrow because I'll have another video starting Chapter 8. Tomorrow during the day, I'll be posting your Chapter 8 slides. And like I said, we'll have a video kind of introducing that and talking about Chapter 8. So if you need anything else for your roller coaster, make sure you bring that in. I'm pretty excited to see what work that you do on them tomorrow. I will see you guys tomorrow. Have a really wonderful night. Bye.